Hello, good afternoon. This is the master thesis defense of Kaloyan Ganovsky that studied last academic year in our master. The title is Artificial Neural Networks Through the Lens of Dynamical Systems Theory. And the jury is composed by Dr. Lucas Lacasa as vocal, Dr. Samin as secretary, and myself as president. So you can start whenever you wish. And you know that if possible, don't use more than 20 plus minutes.
I will do my best. Okay, thank you very much. I guess, okay, people online can't see this, but that's fine. Okay, hello everyone. Thank you for coming. For those of you that don't know me, my name is Kaloyan, and I'm going to be talking about the master's thesis work that we did for the last 5 months. We just calculated it in close collaboration with Lucas and Miguel, of course. So the title is Artificial Neural Networks Through the Lens of Dynamical Systems Theory. And the title is quite appropriate because this was simply our goal. We wanted to adopt the perspective of dynamical systems theory and just see what we see when we look at the training process of artificial neural networks. And mostly we're looking at the training trajectories described by these networks in weight space under the gradient descent algorithm, but we'll go into that in a second. So first I'm going to give a little brief introduction, and then I'm going to present some of the main results. Okay. So first of all, I assume most of you are at least kind of conceptually familiar with what neural networks are, artificial neural networks. But essentially they are, abstractly, they're just a mapping from inputs to outputs. They can be conceptualized as a number of distinct computational units, neurons, organized in layers where we say that the first layer is the input, the last layer is the output, and everything in between, in this case just one, is a hidden layer. And mathematically, it's just a composition of nonlinear functions and affine transformations, where the transformations take the outputs from a previous layer, do a weighted sum with this weight matrix here, add a bias term, so-called bias term, and feed all of that through a nonlinear function. We're specifically going to be looking at the sigmoid nonlinear function. So of course, to make this mapping approximate some kind of function, some kind of pattern, we need to train it. We needed to learn some patterns generally from empirical data. And to do this learning, we frame it as an optimization problem, and we apply, in principle, any optimization algorithm. In this case, we use gradient descent as kind of the simplest example that's still applied in the literature. And the gradient descent is very simple. We are defining a loss function, of course. This is what we'll use. This is called the cross entropy loss. But in general, we define the loss function, and the gradient descent simply takes our parameters in the direction of steepest descent towards a minima of that loss function. So this is what we do here. We iteratively apply this algorithm, and we say a weight at the next iteration or the next time step is simply the weight at the previous minus the loss gradient weighted by a parameter called the learning rate. And this is kind of our only hyperparameter in this model, and it's going to be quite important. And all of this defines our gradient descent map. So the motivation behind looking at this in the first place is that we can define this, and we know that neural networks do well, but we want to understand more about why they perform as well as they do. We want to understand what's actually happening in this weight space during the training process. Okay, so I mentioned we need some kind of task, something to train the network to do. And the task that we use in our work is the so-called iris dataset. It's a dataset that contains information about the physiological properties of different plant specimens of one of 3 species. So the goal of learning this task is to classify one specimen in one of the 3 species based on 4 parameters, 4 properties, and you can see a 2-dimensional representation here. And it's a very small data set, 150 samples, like very, very small compared to real life machine learning problems. And it's very easy. It's used for calibrating like machine learning models. And the network that we kind of designed, the network architecture that we use, sorry, I'm in the way for some of you. The network architecture that we use is we just use a single hidden layer of 10 neurons. So in the end, we have one layer of 4 neurons, that's the input, one layer of 10 neurons, that's the hidden layer, and one output layer of 3 neurons. And those 3 neurons essentially represent a probability distribution over the 3 classes that we want to classify. But even with this, we have more than 80 parameters, which for studying dynamical systems can be considered kind of high dimensional, although for machine learning models, it's nothing. And I mentioned already, we specifically use the cross entropy loss. That's a standard choice for multi-class classification. And we use the sigmoid activation. And even with these already, the loss function is very non-convex. That's kind of trivial. If it was convex, we wouldn't be here talking about how to solve it. And in general, you can change this architecture to get a better, to calibrate your model to perform better. But in our case, we keep them fixed. And the last important point is that I mentioned you use this data to calculate the loss, so you can train the network. In general, you sample the data set, the training data set, to perform your iterations. But in this case, we don't sample, we use the whole data set. So our algorithm, the map that we showed here, the gradient descent map, is actually fully deterministic. And that's going to be useful. Okay, so now this is where the dynamical systems comes in. How are we going to study this? So we say we have our gradient descent map. We take iterations of it. We apply it again and again. And from that, we take, we extract a trajectory in weight space over time or over iterations. We're using T here. And then we're also looking at, we have a perturbation scheme. So we take one point in that trajectory, for example, the initial point, and we perturb it by adding a small uniform random number in the range minus epsilon, epsilon. And this epsilon is our perturbation radius, and we're going to be talking about it quite a bit. And then we're going to look in general at the distance between these trajectories, let's call it a reference weight trajectory and a perturbed weight trajectory, which is defined by a perturbation evolved independently from the reference. So we're going to look at this distance, which we take simply as the absolute value of the difference element-wise. And we're going to draw on some literature to guide our intuitions here. We're going specifically very simple dynamical systems, linear stability theory, and a generalization of orbital stability. And our starting intuition for this, even though there's not a lot of work in this, there's not a lot of literature to guide us, our starting intuitions were that the solutions that are reached by applying this gradient descent algorithm iteratively essentially represent stable fixed points of the dynamics of the gradient descent map. And also, we assumed that the dynamics would heavily depend on the learning rate parameter of the gradient descent. Specifically, we thought that for small learning rates, we see more or less gradual convergence, and maybe we would see orbits be stable or attractive. So when we perturb, the perturbation was going to exponentially decrease. The distance would exponentially decrease. Whereas for large learning rates, we weren't really sure what to expect, but we thought the convergence is probably going to be more regular. It's not going to be guaranteed that we find the minima, and maybe we'll see some chaotic-like behavior. But okay, first, we're going to go into the results. First, we'll look at the small learning rate regime. And let's just see what we see when we adopt this perspective. Here, we're plotting the distance over time or over iterations for 3 different initial conditions, completely independently drawn. And we're showing here in the gray lines are the distances between a perturbation started at the initial condition and a reference trajectory. And the black line is just the average over those perturbations. And the blue line here is the loss. You can see it on the right-hand axis scale. And we see a couple of things. First of all, it's important to say the network learns, so we're actually it's actually kind of realistic. So We also see that in general, the distances are not necessarily, they have bumps and irregularities. Sometimes they decrease quickly or drop quickly. And in general, in most cases, in almost all cases, but with different speeds, we see a divergence on average of the distance to the reference. And yeah, so this is initially what puzzled us, is why do we see this kind of divergence, and why do we not see essentially perturbations growing back to the distances from perturbations decreasing. And okay, we thought the intuition that we're forming from linear stability theory is that perturbations will shrink, but only very close to the fixed point. So these perturbations here are for epsilon 10 to the minus 8, the perturbation range that I defined before. Oops, I defined before here. It's 10 to the minus 8. What if we look at a different range of epsilon, specifically smaller epsilon? And here we're showing the distance from trajectories evolved from a perturbation at the initial conditions to the reference, but normalized by the value of epsilon and the size of the network, but most importantly, the value of epsilon. And we see that for all, when taking perturbations for this whole range of epsilon, when we normalize this, the distances essentially, well, they don't collapse to the same curve, but more or less they behave very similarly. So the distance scales with this epsilon. And for no values of epsilon here, and in other cases, this is just an example, of course, for no values of epsilon do we see attractive orbits. They always diverge, more or less quickly. Okay, so we say, okay, but if we go back to our initial intuition, it's actually the final solutions that maybe are stable. So maybe perturbing at the initial condition, maybe we don't see any stable orbits or stable fixed points. So we decided, let's train the network up to some point and then take a perturbation, see what happens. So here we do that. We train for 4,000 iterations and then perturb and look at the next 1,000, how the distance evolves. And we see it's quite different from before. In general, we don't see divergence. We see either very slight or very slow kind of shrinking of perturbations, or essentially constant over time. And the one thing we still don't see is these perturbations decreasing exponentially over time, which is what linear stability theory would tell us. But this is essentially what we're looking here is a case of marginal stability, because these trajectories don't diverge exponentially, neither do they shrink, so they kind of remain bounded in a neighborhood of the kind of reference orbit. So this volume doesn't go anywhere really. And this is kind of analogous to saying that the solutions that we reach are not individual points in the weight space, but they're represented by very high dimensional manifolds, which means that some dimensions, some weights don't matter as much for the loss and for the output of the network. Therefore, taking a perturbation along those dimensions has no gradient, and therefore will neither shrink nor increase over time. This is what we're seeing here. Okay, now moving on to what happens when we bump up the learning rate a little bit. Here we go from, well, I forgot to mention, yes, this was learning rate of 0.1. Now we go up to 1. And here our network reaches a regime which is termed the edge of stability, not by us, but by some other authors. And these Cohen and colleagues, and also a couple of other researchers, they identified this regime as one where essentially you can think of it as the convergence of the gradient descent is almost stable. It's hovering on the edge of stability, and the loss, which we see here on the right, the loss is no longer monotonic as we saw before. no longer monotonically decreasing, I mean. Now it's very highly irregular, but in general, it's actually quite efficient. So we very quickly reach optimal solutions, let's say, or near optimal solutions. And what's interesting from a dynamical systems point of view is if you look at this second column here, these are the evolution of the distance between a reference and perturbations over time at the very start in log linear scale. And we see that in many cases, well, you know, not in some, but in many cases, we see a kind of exponential divergence. And okay, well, we can quantify this. In general, you know that if we have a divergence of this form, where it's exponential from some initial distance, the exponent here is called the Lyapunov exponent. And we can estimate this empirically in the following way. First of all, we take a lot of different initial conditions, and we calculate the average distance between those initial, between orbits from those initial conditions and very nearby orbits or perturbations in our case. And this is this big lambda here, which is a measure of the kind of local Lyapunov exponent for different initial conditions. If we do that for a lot of initial conditions, we get a distribution like this. And taking the mean of that distribution, which, you know, it tends to a kind of normal like if we're lucky, and in this case we are. If we take the mean of this, that's an estimate of the maximum Lyapunov exponent, which is a global quantity. And if we look at those means and standard deviations in this case as a function of epsilon, we see that as we decrease epsilon, which is the limit we're interested in, the maximum Lyapunov exponent has a kind of limiting value, or we can assume it tends towards some value. Okay, so that's interesting. Let's bump it up even further. We have a learning rate equal to 5, which is way larger than anything you'd see in practice used. But still, what do we see? So here we're showing the time series of just the loss for a bunch of different initial conditions. And most of the time, what we see is two different types of behavior, which are exemplified here by these two trajectories. In one case, we kind of have chaotic-like, very, very irregular behavior. In the other case, we have a kind of periodic-like. I call it quasi-periodic, although I'm not using that term in its technical sense. And I can talk about that later if you want. But these two regimes are what we see most often, and the trajectories tend to switch between these regimes like this. And okay, we can look at this and say it looks kind of, maybe it could be chaotic, but we can actually test. So looking closer, this is the trajectory. The same was in the previous slide. This is just the first 50 time steps. We can look at this and say, okay, it looks very irregular. But we can test by looking at the autocorrelation function. I'm assuming most of you are familiar with what that is. And here's what we see. It's kind of difficult maybe for you to see, but there is a little band here around 0, which is our 95% confidence interval for a fully randomized null model. So we shuffle the series and we calculate the autocorrelation function. And we see that the autocorrelation function for our actual series shows correlations that cannot be attributed to a random process, right? So there is some dependence that is not really random there. Also, we can look at the distance between nearby orbits in this series, and this is what we see. Essentially, after the first time step, the distance goes straight to the kind of size of this attractor. We don't see any exponential divergence. Which this is what we would expect to see from a kind of truly random series. So, I mean, it's not really chaotic-like, it's not really exactly random. We're not, actually at this point, we're not really sure what it is, but it's kind of interesting for sure. But yeah, so this was kind of the main results. And to wrap up, I want to try and kind of bring it together because our work was more exploratory. I mean, I've shown only a small subset of all the questions we tried to explore. But in general, we can talk about, or at least in my head, the way I organize this is, we can talk about two key themes. One is stability. So we saw that our initial expectations that we might find stable orbits were kind of validated in the sense that we found marginal stability when we took perturbations closer to the solutions. But this regularity with epsilon that we saw, so the size of the perturbation, didn't really affect the stability of the trajectories, which what I mean by this is that for small epsilon, we didn't see attractive orbits, essentially, which was kind of surprising to us. On the other hand, when looking at the sensitivity, we saw that in general, when we perturb at the initial condition, we see divergence over time. So we don't see this volume of perturbed trajectories shrinking. So it heavily depends on the location in weight space. And for larger eta, we actually managed to quantify a sensitive dependence on initial conditions in this edge of stability regime that I showed earlier. So is there anything in the literature that can actually help us understand this? Yes, a little bit. There is results in like optimization theory and like deep learning theory that kind of can give us some insights into this, although none of them really adopt this perspective explicitly. And there's some hints to potential applications. Unfortunately, our time is kind of limited, so I couldn't include all of that here, but of course we can talk about it in the questions. And the importance of this work, well, I think it was nice that we managed to validate some results in deep learning theory, like, for example, the finding that minima, the solutions of neural networks after training, are not points, but they are large, high-dimensional basins. That's something that, in hindsight, we found out was known in the literature, but it was nice to validate that. We also found some new results related to the chaotic behavior for larger learning rates. And most importantly, I think this allows us to ask more targeted questions when we look at this perspective in the future. And speaking of the future, I think there are two like broad directions that you could take this research. On one hand, you can keep studying cases like we did here of very simple architectures and try to really formalize the dynamical systems tools. And also study maybe the effects of different choices of architecture. On the other hand, you could also study more real-world architectures, so a couple of million parameters rather than 80 parameters, and see if dynamical systems can tell us anything about what's going on in the training process there, if it can have any practical applications. And just finally, zooming out a little bit, is there anything we can tell about the potential of this framework at this point for improving our understanding of the training of neural networks? I mean, it's a little bit early. As we said, this is just kind of preliminary explorations. But the biggest advantage, the biggest benefit that this framework could have in our view is that it could bring a more principled perspective to understanding the training of neural networks, in the sense that maybe we could identify some general conditions under which training trajectories are stable or show chaotic behavior and things like that. And maybe it will be able to provide a kind of unifying view to bring together some results that are currently scattered amongst optimization theory, applications of neural networks, and other research that if you spend some time researching in this space, you'll know it's quite difficult to reason about. But yes, that's all from me. Thank you very much for your attention. And also, I just want to thank Lucas and Miguel for all of their support and everything throughout this thesis. Thank you very much.
Thank you for this.